Well, hey, it's Dr. J. Today we're going to learn a graphing strategy using the first and the second derivatives, f prime and f double prime, first and second derivatives. So there's some key characteristics that I talked about in the last couple videos with the first derivative test and the second derivative test. And today we're going to get more into how those results can help us build a picture of the function in a more accurate and hopefully more efficient way than it probably would have been presented in an algebra course. So none of these graphs today are new. They're all things you would have seen in a college level algebra course or perhaps a pre-calculus course or something of that nature. But my intent today is to not really show you new images. They'll all be things that you hopefully have seen before, but a new way of looking at the images and in particular constructing them hopefully very easily now that we have these tools. So a couple things I want to mention about what the derivatives tell us. They tell us, so f prime of x, I'm going to say, now, x could be any real number, but for the sake of simplicity, I've sort of limited my x values here on the grid already. So I won't be going very far away from the origin in this particular presentation. So f prime of x tells us where the function is increasing or decreasing. Yeah, so increasing or decreasing based on its sign. Yeah, so f prime of x being greater than 0 tells us that the function is increasing. F prime of x being less than 0 tells us that the function is decreasing. And then if it's actually equal to 0, it's neither. And so this is called a critical value. It means that it's neither increasing nor decreasing, and we need more information to determine what it is. Okay. The second derivative of x tells us the concavity. So for example, if the second derivative is positive, then that means that the graph is concave up. In other words, it's shaped like the letter U. If the second derivative is less than 0, it's concave down. And we can use this information in conjunction with the first derivative to tell us the importance of this critical value. So for example, if the critical value produces a second derivative that's positive, then that would mean that it was shaped like the letter U, and we would have what we call a local min, or a local minimum. If the critical value produces a second derivative that's concave down, it's negative, so it would create a local maximum. And I'll draw some pictures of that in just a second. Okay. And then when f double prime, I ran out of room down here at the bottom, but coming up here to the top, if f double prime of x is equal to 0, now I always called these critical values, when I was growing up, it was another type of critical value. And we could still call them that. Anytime that a derivative or a second derivative is equal to 0, it is a type of critical value. But what I called them was PIVs, or possible inflection values. All right, and then we would need more information. We would need to test to see if it is a genuine, what we call IF, or IV, not IF, inflection value or inflection point. Sometimes we refer to it as an inflection point. I do use the word point pretty loosely. The true definition of a point is an X and a Y value. I won't try to trick you. If I want both X and Y, I will specifically ask for it. But I'll get more into the details as we do some examples. Okay, so once we find the X value, I usually say at X, whatever that value ends up being. For now, I'll just put question mark. In this example that I'm about to do, it'll be one of these values here. All right, so that's the brief introduction to the strategy. The strategy, I hope, will become more clear as we do an example. So let's see example 1. Given the graph, state the facts about f prime of x and f double prime of x at the specified point. So we'll do something like, I don't know, and again, I don't really care too much about the y values yet. I mean, I will at some point, but for this example, we'll say that this function is y equals f of x. All right. So what are some facts? What do we know about f of x at this point, or at this specified value? So x is equal to 2 at this value. I'm not really caring about y, right? I'm saying it's this point, but all I really care about right now is the x value. It's a function of x. So at f of x, because this is a local maximum, we know that f prime of 2 is equal to 0. Yeah. And because it's concave down, we know that f double prime of 2 is less than 0. So just the facts. These are the facts about the first and second derivative at the specified point. Okay. Now, what happens if I change the point? Say this example 2. If I change the point, same question, new point. So let's change it to, say, here. So, tell me the facts. Well, it's no longer a local max. Yeah. It's not a critical value. The derivative is not equal to 0. Yeah. But it is decreasing. So I know the first derivative is negative. Now the concavity doesn't change for this particular shape. Yeah, this is a concave down, parabola, also known as a quadratic function. So that's still going to be true. Concave down. So f double prime will also be negative. All right. I'm going to do more specific examples later. If I turned this upside down and made it, point up, then the results would change, but they wouldn't change very much. Concave down would just be called concave up if it went the other way. Let's do a new function. Say example 3, new function. Say g of x, but same question. So let's do g of x, something like that. So just the facts. So this time our x value is -1. So x equals -1. What do we know about the function? Well, it's not a local max, but it is a critical value. It's not a max or min, though. It's a critical value. So f prime of -1 is equal to 0 here. In other words, it has a horizontal tangent. Going back to the very beginning of the definition of a derivative, right? It's a tangent line. If I were to draw the tangent line, it would be a horizontal line passing through that point right there. But it's not a max or a min because you can see it's going higher. The graph is going higher above this point here. You can't really see it off the screen, but it's going up like that. All right. So we know that the first derivative is equal to 0. That's f prime. And it's changing concavity. It changes from concave down. Say CD, I guess. Yeah, it's concave down on this side, and it's concave up on this side. Say CU for concave up on this side. So it is changing concavity at that point, which is called an inflection point. Now again, I'm going to repeat myself a lot today, but technically the point has an x and a y, but I'm just giving you the x value because that's the most important value. If we needed the y, I could always go back and get it if it was necessary. So that means that f double prime is also equal to 0. So this is a critical value and an inflection point, or IP inflection point. Sometimes I call it an IV, inflection value. Or I could say all of it, the value where the inflection point occurs. All of those things. All right. And let's do one more of these, and then we'll get some more specific equations. These are all just sort of pre-made examples, prefabricated for your enjoyment. Sort of we call these icebreakers in a lecture setting. So same function, new point. Let's move the point over to I don't know. Where should we move it over to? How about right here? All right, so this time it's x equals 0. We usually don't label 0 because 0 is considered an obvious point that doesn't need a label. It's the center of the grid. So what do we know about that point? Well, we know it's concave down at that point. Yeah. And we also know it's decreasing. Yeah. It's not a critical value, though. Yeah, because the derivative is not 0 at that point. It's close. It's close to the derivative being 0, but it's not exactly 0. Right. So we know that the second derivative, or the first derivative, is negative, yeah, because it's decreasing. So it's concave down and decreasing. So this is decreasing, and then this is concave down. All right. Now that's just really the introduction. I'm going to draw some more detailed graphs. Let's do an example where the function, oh, shoot. Correction. Not a big deal. Minor correction before I erase the board, before I get some emails from you. The function was called g. So this is g prime, g double prime, g prime, g double prime. I caught that right before I was about to erase it. How about this? For the rest of the examples today, let me look through my notes. I think I'm going to call everything f. I am. Because I always screw that up. There's really no need to have different function names unless you have two functions happening, next to each other. You don't really need two different names. I thought I would be fancy and change the name to G, and it almost bit me. All right, well, enough of that. Let's move along. All my answers are still correct. Just make sure that I'm talking about the right function. Let's just see a precise or a specific function. One that's given by an equation. So example 5. So given the function, now this is a pretty common function from algebra. It's a quadratic function. Something like that. All right, now again, you could have drawn this function using algebra, and I hope you still can. If not, if it was always something you struggled with or something you just hoped that you got right when this was in an algebra or a pre-calculus level course, this was pretty standard. I would call this a bread and butter function, not very exotic, pretty boring, but useful. Sometimes the most simple and boring things become the most useful tools. I call it bread and butter, but if you're starving, bread and butter is very useful. It can really save you in a pinch. So let's go ahead and do some calculus. So we start with the first derivative. All right. We're not going to do anything with the original function until we want to get the y values, which I will at some point. So let's start with the first derivative. So that'll be what is that? 2 times, I'm going to write it all out. 2 times 1/4 times negative 1/4 x to the 2 minus 1. I know I'll never do this again, but I'm just getting started. Plus 2. Yeah. The derivative of 2x is just 2. And then technically minus 0. The derivative of negative 1 is 0. Generally, you don't write all of this. You've seen me do this before. This is just the cloud. Generally, you will jump right to this step. And there's your first derivative. Okay. Notice 2 times negative 1/4 just becomes negative 1/2. The exponent, 2 minus 1, just becomes 1. I don't even bother writing it. And then I don't write minus 0. So now we set the derivative equal to 0 to find the critical values. All right. This is only going to have one critical value because it's only has one solution. So solve this for x. If you're good at guessing, you know the answer. It's 4. Right? Can you see it right here? It's going to be 4. If you can't see it, well, find it. Subtract 2 from both sides. So get negative 1/2 x equals negative 2. Now, normally I divide, but because this is a fraction, I'm going to multiply by the reciprocal, negative 2 over 1. It's the same as dividing, multiplying by the reciprocal. And then that'll cancel all this stuff out. The negatives over here will cancel, and I will get negative times a negative is a positive 4. And again, technically, you know, it's 4 over 1, but I'm not going to write that. I'm just going to say x equals 4. So that's my critical value. Right there. All right. Now, I don't know anything else about it except for that it's critical. In other words, f prime of 4 is equal to 0. Yeah. That's all I know for now. Okay. So now to determine whether it's a maximum or minimum, I need the second derivative. All right, so let's do the second derivative, f double prime of x. Well, because this is a linear function, negative 1/2 x plus 2, the second derivative is just negative 1/2. Right. You know that rule from the basic rules of derivatives. So, f double prime is negative. That means it's concave down. Therefore, the function has a local max. Yeah, concave down looks like this. So it's a local max of blank, I'll put a question mark, at x equals 4. And now I need to find that local max. So we're going to use the original function, which I kept up here. So f of 4, this is not calculus anymore. This is just algebra. Plugging in 4 to figure out what the y value is. Sometimes we call it y max. Just an abbreviation for the maximum y value. It's negative 1/4 times 16 plus 8 minus 1. Let's try to do this with mental math. Negative 1/4 times 16 is 4. Is negative 4. Negative 4. Negative 4 plus 8 is 4. 4 minus 1 is 3. So there is a local max of 3 at x equals 4. So 1, 2, 3. I'm doing a two squares equals 1 unit scale, mainly so that the audience can see it. Put my first dot right there. That's my local max. And then I'm going to add any other point that I like. any other point I like. So first point is for 3, then plot any point of your choice. And I really mean any point of your choice, but it has to be true. Sometimes people watch my videos and then they'll say, well, Dr. Jordan, you said I can plot any point I want. So they'll plot this point, and remember, you're going to be doing this with your mouse, and then they'll just click anywhere they like because they heard me say you can do anywhere you like. It's any point that you like that's true. It has to be a true point, right? It has to actually satisfy the original function. It's a lot of erasing today because my board takes up half, my graphing board takes up half the whiteboard. So any point of my choice, I'm going to go with 2. If you want to choose 3, you can, but you might not like what you get. You are allowed to choose it, though. You'll end up with fractions, and you'll regret that choice. So I'm choosing something that's going to hopefully prevent a fraction. So 1/4 times 4 plus 4 minus 1. 1/4, negative 1/4 times 4 is negative 1 plus 4 minus 1 is 2. Oh, that's neat. 2, 2. So that is the point of my choice. 2, 2. And then so my graph will look like this. There you go. The software that I use only allows you to plot 2 points. So this will be your first point. Click on the second point, and then the graph will automatically create itself. All right, there you go. Not too shabby, huh? Notice this side kind of went off the grid. So that's kind of what it would look like on your screen, because your screen would cut it off right about there. I mean, if it was this particular problem. All right. That's probably the easiest graph we're going to do today. So I should probably shut up and move on to the next example. Example 6. F of x is, I'm just going to call everything f of x today so I don't screw this up. 1/2 x cubed plus 3x squared plus 6x plus 5. All right. Yeah, I considered getting a smaller one of these. I got it coming on Amazon, and we might be using that. And then I have a spare grid over here. I'm not sure how, this one's kind of dark though. So I don't know. I'm just going to keep using this one for now. All right. So again, just get started. This is calculus. So we take derivatives. If you're taking a test, you don't know what to do, think, hey, what class is this? This is calculus. Take a derivative. All right. Good place to start. Now you could show all the steps. I've done that in the previous videos. I'm going to spare you the details, and I'm just going to do it. 3 times 1/2 is 3/2, or if you prefer decimals, 1.5 would be okay as well. 3 times 2 is 6. That's going to be 6x. And then this is a 6x. The derivative is just 6. And then 5, the derivative is 0. So that's your derivative using mental math, which, you know, this is week, 10 of the semester. Hopefully your skills are improving. You know you're going to need the second derivative. You might as well just take it now. I usually just stack them right next to each other. 2 times 1.5 is 3, and then that'll be x. And then the derivative of 6x is 6. and the derivative of 6 is 0. So there's your first and second derivative all ready to go. Okay. So when you solve for the first derivative equaling 0, it kind of sucks, but it's not that bad. I probably would not do anything more complicated than this for the first derivative, but this is something we could probably handle. What we'll do is we'll multiply everybody by 2. And that'll make the fraction go away. Right, and then we'll divide everybody by 3. That'll make this leading coefficient go away. Then we'll factor it. If it's not factorable, I always could use some other formula, like the quadratic formula or the completing the square method. This one is definitely factorable. 2 times 2 is 4, and 2 plus 2 is also 4, so you get 2 copies of the same factor. When you get 2 identical factors, you don't have to solve them both. Just pick one of them because they're twins. All right, you're going to get 2 copies of the same answer. I don't need to see both copies. Just one copy will be fine. And you're going to get x equals -2. All right, I did that with mental math. That should be pretty easy. I don't know if you could see that way back here, that x equals -2 was the solution. This one was not very obvious. All right, so that's our critical value. All right. Now, I don't know whether it's concave up or whether it's concave down because I have to look at the second derivative for concavity. All right, the second derivative tells me the concavity. So let's plug in -2 into here. And what do you know? You get 0. So f double prime of x is equal to 0 when x is equal to -2 also. That means it's an inflection point. So I've got an inflection point at -2. So coming over here at -2, I need to find the y value where it's inflecting. Remember, inflection means it's changing concavity. Okay. Now, I said this earlier, I'm calling this an inflection point, but I don't really know the whole point. I only know half of it. I only know that x is -2. I got to figure out the y value. What's the y value equal to? Well, I'm going to have to use the original function in order to do that. One strategy I'm going to use probably after this example is I'm going to remove the grid until I'm ready to draw the graph, because as you can see, the grid is taking up quite a bit of my real estate. So I know that I have an inflection point at -2, which is fine, you know, for now, but if I want to finish the problem, I need to know the y value. So I'm going to plug it into here. 1/2 times negative 2 cubed plus 3 times negative 2 squared plus 6 times negative 2 plus 5. So it's going to be my y, right? One half times negative 8, 3 times 4, negative 12 plus 5. I sure hope it fits on my grid. Otherwise, I might have to change my scale. Negative 4 plus 12 minus 12 plus 5. Oh, so the 12s cancel. Whew. And negative 4 and 5 is 1, so it definitely fits. Y is equal to 1. That's nice. So right here. All right, so that is the inflection point. And if I really wanted to be precise, I would say the inflection point is negative 2, comma 1. Yeah, or I could say the inflection point is at negative 2 and y equals 1. All right. Now, what does an inflection point mean? Inflection means it's either changing from up to down. Yeah, that's an inflection point. Or it could be changing from down to up. Right? And you always think of it as you're moving from left to right. So as you're moving from left to right, this function is going from up, concave up, to concave down. In other words, positive to negative. Or it could be going the other way. It could be going from down to up. In other words, negative to positive. All right. So remember, down means that the second derivative is negative. Up means the second derivative is positive. Right? Down means the second derivative is negative. Up means the second derivative is positive. And do you remember how easy the second derivative was? I erased it, but the second derivative was super easy. It was 3x plus 6. A very easy equation. I'll say recall. You probably still have it in your notes if you're taking notes. If not, rewind the video. Make sure I'm right. If you don't do that, then I could screw this whole thing up. Let's double check. 3 times a half is 1.5, and then 2 times 1.5 is 3. Good. And then 3 times 2 is 6, and then the derivative of 6x is just 6. So that is correct. All right. So if I test a number to the left, why am I pointing to the wrong side? To the left, negative 3, or to the right, I could test whether it's going down, up, or up, down. So let's just test a single number. How about negative 1? If you like, you can also do negative 3. Once you've tested one number, the other number is going to be the opposite. That's going to be 3 times negative 1 plus 6, which is negative 3 plus 6, which is 3. This is positive, so it's concave up. So that means this is the winner. Yeah. I'm not going to do it, but had I tested the other point, negative 3, I usually do one on the right and one on the left. It would have just came up negative and it would have been down. All right. So I know my graph looks like this. It's concave up on the right and it's concave down on the left. Now I need one other point of my choice. It must be a true point of your choice. All right. I might as well just do -1, actually, I changed my mind. Let's do 0. -1 would have been okay, but I would have got fractions. And fractions are okay. You play around with the mouse and see. It'll typically let you do halves. That's about as many fractions as you can do. So you can do 1.5, 2.5, 3.5, things like that. You can go between the numbers, but that's about it. 0 is always a very nice number, right? Because notice when you plug in 0, I'm done. I'm just going to get 5. Yeah, that's going to be 0. That's going to be 0. That's going to be 0. And I'm just going to get 5. So I'm done. Y is equal to 5. So there's 0, 5 right at the top. Click on your second point right there. You got to have at least 2. You got to have exactly 2 true points in order to get the graph to stick. All right. Well, I learned my lesson. I thought I would start this video, by having the grid all out and labeled and numbered and everything. Mainly as, the introduction to the section on graphing. This is my strategy. But now I'm going to do a lot more writing. So I'm going to have to remove the grid and then pull it back in when we're ready to graph. So for the next few examples, 1, 2, 3, 4. Oh man, we got a while to go. I don't know if I'll get them all done in this part, but we'll try. So for the next few examples, let's remove the grid. Until I have some stuff to graph, which means we're going to have to document all of our results very carefully so that at the very end I can just plop the grid down in the center and we can just draw the graph with everything that we've learned. All right, they're going to get a little harder now. The next one is still a cubic. It's still a cubic, but it's going to be a little more complicated. All right, you're going to see right away what happens. So let's get into it. Let's go ahead and take the first derivative. That was almost too easy, yeah? 3x squared minus 5. Let's go ahead and take the second derivative. 6x. Also pretty easy, yeah? All right, so let's find the critical values. Critical values, we set the first derivative to 0. There's several possibilities that could happen here. It could be factorable, like it was in the last one. This one's not factorable, so I'm just going to solve it by using a square root. That's because there's only 2 terms, 3x squared and -5. If it had 3 terms, if it had 3x squared and then, say 6x plus 12 or something, then I would have used quadratic formula or something like that. 5/3, not 5/2, 5/3. So x is approximately, I didn't bring my, I have it right here. There we go. So we're going to take the square root of both sides. 5/3 square rooted plus or minus 1.29. Let's do 1.3. I know I change my tolerance depending on the problem because we're graphing. 1.29 and 1.3 are essentially the same thing, so it's not really going to matter that much. I will tell you what to round to if you have to round. All right, so there's my CVs. X equals negative 1.3 and positive 1.3. Oh, God, drop my phone. I didn't break it. All right, so let's do a test. Let's save this for later. That'll be easy to come back to. So let's do the test. Negative 1.3, positive 1.3. This is your first derivative test. It's also known as a sign test. Positive and negative. So what you do is you take a number in the middle, say 0. You take a number on the right, say 2. You take a number on the left, say negative 2. These are also known as partitions, so I draw these lines here. And I test whether that's positive or negative. Now remember, I don't really care what the answer is. I just care whether it's positive or negative. So 2 squared is 4. 4 times 3 is 12. 12 minus 5 is positive. Yeah. 0. 0 squared is 0. 3 times 0 is still 0. 0 minus 5 is negative. And you probably believe me that this one's also positive. I'll leave it to you to check. DIY. If you plug in negative 2, even though you're plugging in a negative, you're going to square it and it's still going to come out positive. All right. So that means that the graph is increasing from negative infinity to negative 1.3. Union 1.3 to infinity. And then it's decreasing from negative 1.3 to 1.3. So that's all the first derivative. That's just a review of what we did last time. All right, so now we have the second derivative, f double prime of x. Much easier. That's just 6x. Let's set that equal to 0. Set it equal to 0 and solve. Not a big surprise, you get 0. So this is your possible inflection value, PIV, or some people call them PIPs, possible inflection points. If you're sure it's an inflection point, you can just say so now. I'm saying it's possible. Yeah. So now we're going to test the second derivative. You could try to do it right here. It gets kind of messy. I have seen people double dip their sign test, but I'm just going to make a new sign test, starting with 0. So pick a number on the right. Say 1. Pick a number on the left, negative 1. And this time you're testing the signs of the second derivative. You could actually use these numbers if you like. I just picked nearby numbers, 1 and negative 1, because they're easier to plug in. But I mean, you could pick those as well. That's fine. I've done that before. Use the critical numbers as your test numbers in this one. What's cool about that is you get kind of a 2-for-1 deal. It tells you not only the concavity, but it tells you whether it's a max or a min. And remember, this is a sign test, so I don't actually have to use my calculator. I just have to plug in the number and tell me whether it's positive. So 1.3 times 6 is positive. That's all I care about. Negative 1.3 times 6 is negative. That's all I care about. So that means this is concave down and this is concave up. It also tells me that this is a max. Sorry, this is a min. And this is a max. It's a little bit backwards. If the graph is concave up, I like to actually draw the letter U. It reminds you that's a min. If the graph is concave down, draw an upside down U, that reminds you it's a max. It's easy to get those backwards if you're just working sort of mechanically. All right. So it's going to be concave down, negative infinity to negative 1.3, concave up, 1.3 to infinity. Oh, sorry. Not 1.3. I'm looking at the wrong thing. 0 to infinity. So the partition line tells you where it changes concavity. Don't let the 1.3 screw up your head. Those were just the test numbers. They don't go into your final answer. They do up here. Yeah, because those are your partition numbers. So the partition numbers are always the numbers that go into your final result. All right, I think we have everything. So let's write this down. Even though the function is called f, I'm going to just call it y because it takes less space to write. I'm going to try to squeeze all this stuff into one nice little thing here. Let's see. So I've got a max of blank at negative 1.3. I'll figure that out later. I've got a min of blank. I'll figure that out later at 1.3. I want to erase all this because I'm bringing my board in. I've got increasing from negative infinity to negative 1.3 union. That's not going to fit. I got decreasing from negative 1.3 to 1.3. I've got increasing from negative infinity to negative 1.3 union positive 1.3 to infinity. And I've got an inflection point at 0, I don't know. I have to figure that out. Right? So now I can erase all this. All right, now you're going to, once you've gotten all of your data or information from the derivatives, go back to the original function to fill in these blanks here. Probably going to need a calculator. Oh, you won't need a calculator for this one. That one's going to be easy. 0 cubed minus 5 times 0 plus 2 is just 0, 2. Yeah, that one was easy. You'll need a calculator for these other ones. Sometimes this is called y max and y min. Just a way of noting that you're finding the y value. So I got 1.3 cubed I'm going to write it all down in case I screw this up. And then I got 5 times 1.3, 6.5, and then plus 2. So I'm going to do negative 6.5 plus 2 plus 2.197. And that's going to be negative 2.3 will be fine for us. Now watch. This was, oh, actually, no, that was this one. That was my min. So this one's the one I just did. Now this is, I call this a BOGO. Buy one, get one, right? Only if they're just opposite numbers. You know, you can save yourself a little work, all right? Just change this to a negative, change this to a positive, and you don't have to plug them all in again. I mean, you still need to do some basic math, but you don't need to use this again. You've already got them right here. So you're going to go 8.5. I did that in my head. And then minus, so 8.5 minus 2.197. And I'm going to get 6.3. You see how I got the BOGO, the buy one, get one for this, for the negative? When you plug a negative in, it's a negative number cubed. Well, that's going to be the same value, just negative. And then when you plug a negative into this part, negative 5 times negative 1.3, again, it's going to be the same value. It's just going to be positive. Right? Now, if you don't feel comfortable taking the freebie, then do it all and work it all out, and then you've earned both of them. But if you notice that there's a similarity there that you can take advantage of, I encourage you to do that, as long as you're right. Sometimes people try to take a freebie and it's not right, and it causes problems. Okay, we are ready. After all that, we are ready to draw our graph. Let's see. Now, you don't get to choose your scale. I probably have the scale chosen for you, but I'll choose it appropriately so everything will fit. So let's see. We got the inflection point at 0.2. Right about here. All right. What else do we know? We got a max. So we got 1, 2, 3, 4, 5. Can't do the scale. Gonna have to just do a 1-to-1 scale. So 1, 2, 3, 4, 5, 6. 1, 2. So there's 0.2. Oh, I could do a bigger scale on the X. That's legal. So there's 1, 2, 3, -1, -2, so on and so forth, -3. I don't think I'll need all that. All right, so I've got inflection point at 0.2. I've got a max at -1.3 and 6.3, so right about there. Again, doesn't have to be too precise, just a little bit past -1 and a little bit above 6. All right. And then I got my positive 1.3. My min will be down here at -2.3. So right about here. It's concave up. On the right of the inflection point, and then it's concave down to the left of the inflection point. And so there's your graph. You will not be drawing these with a mouse. So what you'll do is just draw a rough sketch in your notebook. I mean, you could even be this rough, you know, like here's how I would probably do it. This is sort of a rough sketch. And then pick the correct answer. So I'll give you 4 choices. Just pick the one that looks like this. I won't try to trick you. You know, I won't have 2 that look exactly the same. There'll be 2 that are close, but so you'll have to look very carefully at the X and Y values and try to figure out. General strategy with multiple choice is 2 of the answers are ridiculous, and then 2 of them are plausible, and then you have to sort of narrow it down to which one makes sense. So we've come a long way with graphing, with the computers in your generation. You know, when I took a class like this 30 years ago, we didn't even have mouses. I mean, we had computers when I was in college. I'm not that old, you know, but the computers were pretty primitive. You certainly couldn't draw a parabola with a computer back then. They were basically fancy typewriters. And you guys these days have much more sophisticated devices, but believe it or not, you know, here it is. I don't know what year you're going to watch this video in the future. You know, somebody might watch this video in the future and say, well, we have that now. Well, this video was filmed in the spring of 2024. And as of the spring of 2024, for all of you in the future that are watching this, we live in a world now where for more complicated graphs, we still need to use multiple choice or paper. I could have you mail me in your papers or take a picture with your phone. I don't want to do that. I'd rather just have you pick the right answer. All right. So what are we up to? Example 8. So this is a quartic, 4th degree polynomial with decimal coefficients. It's really just another way of writing a fraction. With these larger degree polynomials, the decimals help keep the y values to a more reasonable numbers. You know, so this is 1/10, you know, this is 1/2, 9/10, 8 and 1/10, and 9 and 1/5. And it helps shrink the y values so that you ended up with ridiculously large numbers, which is really just for presentation's sake. There's nothing really mathematically necessary in that approach. So without any further ado, let's get right into it. The strategy has been so well defined. We start with the derivative. You know all the rules of derivatives. This is bread and butter here. Power rule. Just pull the power down, multiply, subtract 1. Pull the power down, multiply, subtract 1. Pull the power down, multiply, subtract 1. And then for these last two, 8.1x, you just 8.1. The x becomes x to the 0, which we don't write. And then 9.2 is a constant. The derivative of that is 0. All right. Now, this is not an easy problem to solve. So setting f prime of x equal to 0 and solving is difficult. So what we're going to do is we're going to wait and do the second derivative first. So we're going to find f double prime first. Very important. I think I give you this hint in the homework to go ahead and wait on that. One of the reasons is any polynomial larger than second degree, so in particular third, fourth, fifth, solving for x is not very easy. It's not impossible, but it's not very easy. So we just wait, and we'll come back to it later. At the beginning of this video, I showed you the relationships between the first and the second derivatives in the graphs. And sometimes if you have an inflection point, a second derivative is easier to then go back and find the point that corresponds in the first derivative, right? In other words, you might get a 2-for-1 deal, right? So you find the inflection point, and then it also happens to satisfy the other derivative as well. So let's go ahead and keep going. Do the second derivative. It's going to be 1.2 x squared minus 3, or technically 3.0 x minus 1.8. And we will set this one equal to 0 and solve. So this is called the PIVs, the possible inflection values. All right. So once I get those, then I'll be able to maybe go back, or not maybe, but definitely go back and deal with the first derivative later. So this is a second degree equation. It does have decimals. Oops, I almost lost one of my decimals, 1.8. So what I'm going to do is multiply the whole thing by 10. 10, 10, 10, 10. Multiply all the terms by 10, and now I don't have the decimals anymore. Now, if you want to leave them as decimals and try to solve it that way, you certainly can. It's not going to be that complicated, but it'd be okay. It would be okay to leave them as decimals if you like. You could also factor out a 6. Yeah, these are all divisible by 6. So that will make the terms smaller. Factoring or dividing everybody by 6. It's the same thing. I should make a little note here that this is really 6/10. Right? Because I multiplied everybody by 6, and then I'm dividing I multiplied everybody by 10, then I'm dividing everybody by 6. That's the same as factoring out 6/10. Right. It's not really going to change the answer. It's just a mental note to be careful about that. So go ahead and factor this. So 2x times x is 2x squared. 1 times 3 is 3. If I make that a -3 and a +1, I'll double check the middle term will be -5. Right? You might want to double check that. 2 times 3 is -6x. I'm just checking. We call this checking the middle, making sure that it comes out to be -5. -5x. And then +1 times x is +1x. And when you check this, check, it is -5x. All right. You can usually guess the first term and you can guess the last term, but the middle term, you don't want to be guessing the middle term. You want to be verifying that that middle term is right. If you're not very good at factoring, or it's been a while since you took algebra, then maybe use a formula, quadratic formula, or there's some software, available that will give you solutions. That sometimes it takes longer to use a formula or to use a computer program. There's some fancy calculators that do it as well. I typically try to avoid those. I've done it a few times, but I try to make problems that are reasonably solvable for the average algebra student, all right. So now we're going to solve this. Now the leading coefficient is technically 0.6. It used to be 1.2. You could verify that it really still is 1.2. 0.6 times 2 is still 1.2. It's not going to affect our answers. Our possible inflection values are only found by solving the two factors, setting them equal to 0. This doesn't have a variable, so it's not going to affect the answers. So I'm going to get negative 1/2 and 3. Or as decimals, negative 0.5 and 3. So these are our PIVs, possible inflection values. I don't know if they're inflection values until I test them. We call that the second derivative test, F double prime test. All right, let's go ahead and do it. I'm going to need to take back some of this real estate. Now, when I do the second derivative test, I could test this. Or I could test this. These are equivalent. So it's really up to you. You can use the actual, full polynomial equation, quadratic equation, or you can use the factored version. It should give you the same result. If it doesn't, then that means your inflection values are wrong, or that your factoring was wrong or something. So we've got negative 0.5 and we've got 3. That's our partition. I like to draw these boundaries here. Remember, it's a sign test, right? So all we care about is whether or not the sign is positive or negative. So I'm picking a number bigger than 0. I'm picking a number between negative 1/2 and 3. So how about 0? These are my test values. And then I'm going to pick a number that's less than negative 1/2, so negative 1. We sometimes call these t values. See, there. If you just want to write the letter T underneath them, that can be very helpful. All right, so remember, these are PIVs. In order for them to be actual inflection values, that it has to change sign. So positive to negative, or negative to positive, or something like that. If it stays the same sign, then that means it was not an inflection. All right, so let's go ahead and plug it in. Now remember, all we care about is the plus or minus signs. So we can do this with mental math. All right, this is meant to be done with mental math. So let's test 4. 4 minus 3, that's positive. 2 times 4, that's positive. Plus 1, still positive. Times 0.6, still positive. So the sign there is positive. All right, test 0. 0 minus 3, that's negative. 2 times 0 plus 1, that's positive. Times 0.6, positive. So you have a positive, and a negative. Well, that's a negative. Yeah. Positive times a negative. Remember, factors are multiplicative. You're multiplying them. I should mention that 0, it might actually be easier to use the original. Because if you plug in 0, you get 0 squared. That's 0. 3.0 times 0. That's still 0. And then minus 1.8. Well, there it is, negative. And finally, let's test negative 1. Plug it in here. Negative. Yeah. Negative 1 minus 3 is negative. 2 times negative 1, that's negative. plus 1, still negative, and then positive. So I have a positive, a negative, and a negative. Well, that's a positive. So that means this graph is concave up, CU, concave down, CD, and then concave up, CU. And so that these are in fact genuine inflection values. What we usually say is there are inflection points at both of these values. Okay. Later, we will find the corresponding y's. All right, later. I've got a lot more work to do. Just for now, we know where they occur. That's good enough for now. Just knowing where they are is good enough. We can go dig them up later and find the actual values. All right, well, I was waiting to solve this equation, f prime of x equals 0. And the reason why I was waiting is because I wanted to find these ones first. And then now, one of these or both of them possibly may also be critical values. Right? We saw that earlier in the lecture, right at the very beginning of today's lecture, that there's a possibility, it's not a guarantee, but it's a possibility that an inflection point is also a critical value. For example, like this. Yeah. This is a critical value that's also an inflection point. So it's changing its concavity. So let's try. We're going to use what's called synthetic division. Synthetic division. If you haven't done this in a while, well, this is just in time for this course. The first time we've needed it at all course. So let's try negative 0.5. Okay. We're trying to find if the derivative is 0. So we're hoping that f prime of x is equal to 0. This is our f prime here. So in synthetic division, you take out all the coefficients, removing the x's, put the coefficients into this division algorithm box here, or division bar, it's sometimes called. You put a 0 here. Then you add. Then you multiply. If you've had algebra in the last few years, you might have seen this process before. And then you write the result right here. Calculator might be helpful for some of these decimals. So I've got negative 0.5 times 0.4. Probably could have done that in your head. Negative 0.2. Then you add plus 1.5 negative. So you're going to get negative 1.7. Then you multiply and put the answer here. So times negative 0.5, 0.85. Then you add plus 1.8 negative. You get negative 0.95. Then you multiply again. Times 0.5 negative. 0.475. Then you add 8.1. And you get 8.575. This is the value of f prime of x. This is your x. So it's basically, if you haven't done synthetic division in a while, it's a way of testing whether or not that value is a critical value. So what do you think? Is it critical? Is it equal to 0? That's what it means to be a critical value. Right? The derivative is equal to 0. So no. So it is an inflection point, but it's not critical. Right? Which means it's not doing this. Right? This is a critical point and an inflection point. So what it means in terms of the shape, it's increasing because it's positive. So we know it's going up. Yeah. And it's changing its concavity from up to down. It's changing its concavity from up to down. That's not what we're looking for. We're looking for a critical value, like a max or a min. That's what we're looking for. So let's try the other number. Let's try 3. Let's try x equals 3. Now that you know the process, I did the hardest one first. So you try x equals 3. You put a 0 here. You add. You multiply. You add. You multiply. Negative 1.5, 1.2 is negative 0.3. You multiply, negative 0.9. You add, negative 2.7. You multiply, negative 8.1. You add 0. Therefore, f prime of 3 is equal to 0, and x equals 3 is a critical value. That's nice. And the other two critical values can be found by solving a much easier equation. So I'm going to document everything that I want to save. I got IPs or IVs. So those are my IVs. I got a CV at 3. Right. Remember, IVs, inflection values, or inflection points. I guess you can call them IPs as well. That's where the second derivative is 0. Critical values are when the first derivative is 0. There might be more, right? I got to solve this equation now. All right. I found 1. I know that 3 is a critical value because this is equal to 0. The last number, called the remainder, it's the same as the output. Yeah, it's the output of this is the derivative that we're analyzing here. If that value is 0, then we call it critical. Now this is solvable, right? It's second degree. I can solve it. Let's multiply everybody by 10. Let's see if we can divide it. No, it's not divisible by anything. Let's try factoring it. No, it's not going to work either. Don't waste too much time on it. If you can't solve it in 1 or 2 minutes, if you can't solve it, use the quadratic formula. Y'all remember the quadratic formula? Negative b plus or minus the square root of b squared. I'm going to need more room than that. So let's try it again. Negative b, negative 3 plus or minus the square root of b squared, negative 3 squared, minus 4 times a times c all over 2 times a. I'm wondering if I gave up on this a little too soon. We'll find out right now. If this square root comes out nice, that means I quit too soon, but that's all right. You know, I want to show you what's up. I don't know. I don't know what's going to happen. 4 times 4 times 27 plus 9, 441 over 8. I think I did quit too soon. Let's see, what's the square root of 441? 21. That's all right. You saw the technique, which is that if you can't factor it quickly, then use the quadratic formula. If you get a nice number inside the square root, by nice I mean a perfect square number, which it is 21 times 21, then that means you quit too soon. You could have pulled it off. So you're going to get 24 over 8, which is 3. By the way, we already have that one. It just told us something we already knew. Or what's 3 minus 21? 3 minus 21 is negative 18 over 8, which is 9/4. Negative 9/4. So as a decimal, that's negative 2.25, right? I'm a math teacher. I shouldn't have to guess at that, but 9/4 for the audience is 2.25. And because it's negative 2.25. I could have also just done 18/8. Look, 18 divided by 8, still the same thing. Oh, of course, it's negative. All right, so that gave me my other critical value. The 3 I already knew was critical, right? I was really just finding the other one, which is negative 2.25. All right, we're rolling now. So let's summarize everything that we know. We have inflection values. We have critical values, right? We don't have the Y values yet. We're going to need those in a minute. All right. Oh, what about increasing and decrease? Oh, we have concavity. So because of the concavity, so we have its concave up from negative infinity to negative 0.5, union 3 to infinity, and it was concave down in the middle from negative 0.5 to 3. So we knew we had 2 inflection values. Remember when we did the test, it went plus, minus, plus? Yeah, I already erased it, but that's what it did. And so now we have increasing, decreasing. I don't know. We're going to have to do a test. So we've got negative 2.25 and 3. We're going to have to do a sign test. The first derivative test, f prime test. I have the long version of the function, or I also have a shorter version of it. Now that I know the factors, it's going to be 0.4 times x minus 3 squared times x plus 2.25. So this is the factored form, right? And the reason why this one is squared is because it occurred twice. Yeah. We had a critical value, and then we found that same critical value again. Right? When the same critical value occurs twice, it means that that factor is being squared. Now, you don't have to do this. It's not required that you write it like this. You could just use this. These are equivalent forms of the same function, the same derivative function. I sometimes use one for one thing and one for something else. So I'm going to test 4. I'm going to test 0. These are my t values, my test values. And I'm going to test negative 3. It's my other t value. As I mentioned, 0, it's actually easier to test this guy. Here. You plug in 0. 0, 0, 0. These will all turn to 0. And then the last term will be positive. So that's positive. For 4, it's actually easier to use this version. Yeah. So 4 minus 3, that's positive. Yeah. Squaring it, still positive. Yeah. Multiplying it by 0.4, still positive. 4 plus 2.25, still positive. Positive, 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 all positive. All right. Similarly, you could have taken the number 4 and plugged it in here. 4 cubed, that's 64, positive. And times 0.4. Right? Now, the reason why I don't do that is because I don't care about the numeric value. I just care about its sign. If you go up here, you're going to be finding the actual numeric value. And then when you're done, you'll go, well, shit, I did all that work, and all I cared about was whether it was plus or minus. All right. Last one down here, negative 3. Again, all I care about is whether it's plus or minus. So negative 3 plus 2.25. That's negative. Yeah. Negative 3 minus 3. That's negative. But when you square it, it's positive. So if you're keeping track, it's going to be a negative squared, a negative, and then this is positive. So you have a positive, a negative squared, and a negative. Altogether, that's negative. Positive times a negative squared is still negative. One way to think of that is you're counting the number of negatives. It looks like there's only 2 negatives, but remember, one of them's being squared. So there's actually 3 negatives. So that one's negative. Now remember, I already did the second derivative test. I did that first, and then I backed up to the first derivative test. So now I know it's decreasing, increasing, increasing. So decreasing is, where's my black pen? Let's do increasing first. Increasing from negative 2.25 all the way to, it's not written very well. Negative 2.25 all the way to 3. Union 3 to infinity. Yeah. When this happens, we don't bother writing the union. We just say all the way to infinity. Okay, we just say from here, increasing all the way to infinity, and you just ignore the 3 altogether. Okay. And then decreasing negative infinity to negative 2.25. All right, I think we got everything we need. We're ready to draw the graph. We got everything we need. We're ready to draw the graph. I'm going to have to cover some of this stuff up. So let's just remember up. 0.5 union. 3 to infinity. Down. Negative 0.5 to 3. Increasing. Negative 2.25 to infinity. Decreasing negative infinity to negative 2.25. Oh, inflection values and critical values. All right, we're ready to draw the graph. Now we are going to need y values now. So y values. Let's see, Let's see how bad the y values are on this one. Yeah, they're pretty bad. So, well, they're not that bad. They're just big. So here's what we'll do for the y values. We'll go like by tens. 10, 20, 30, 40, like that. And then for the x's, we'll do 1, 2, 3, 4, like that. Okay. Actually, we're going to go 1, 2, 3, 4, 5, 6, like that. Oh, no, I changed my mind. They're not that bad. 1, 2, 3, 4. I might regret this, but you've stuck with me this long. All right, so these are our inflection values, all right? So we know that it's inflecting, and then it's a critical value as well. That's a double dipper right there. Right? The 3 is in both categories. It's an inflection and a critical value. So I need to plug it into my function and find the y. Yeah. Okay, got my calculator. So we're going to need to do a little bit of math here to find the y values, because we're going to have to plot them here. And let's start with 3. 3 was the number that I called a double dipper because it falls in both categories. It's both an inflection point, say INF, and it's also a critical value. It might be a max or a min. We'll find out when we get to it. Although, no, it's not. If it's both values, then it's neither. It means it's like this. So this would be x equals 3. Remember at the beginning of the lecture, if it's both, falls into both categories, it's changing concavity. All right. It might go the other direction. Both of these are possibilities for this 3. So let's go ahead and plug it in and find the point f of 3. And I'm just going to have you walk through it with me with my calculator. I'll write things down as I go. So we got 3 to the 4th power. That's 81. I probably could have done that in my head. Times 1/10. So that's going to be 8.1. 3 to the 3rd power is 27 times 0.5. That's minus 13.5. 3 to the 2nd power is 9. 9 times 0.9 is 8.1 again. 3 is just 3, and then 3 times 8.1. 24.3 and then plus 9.2. So add up all of those and that'll give you your Y value. So 24.3 plus 9.2 is 33.5. These guys cancel. And then minus 13.5, 13.5, we get 20. Nice. So I got 3 and 20. So that is my inflection point. All right, that was probably the easiest one. Let's do f of negative 0.5. That's supposed to be a negative 0.5. All right. This is rather exhausting of a method. 0.5 negative to the 4th power. I guess it doesn't matter that it's negative. It's going to come out positive anyway. And then times 0.1. That's very, very small. 0.00625. And then plus. So 0.5 to the 3rd power. Times another 0.5. Now it's negative and then a negative, so that's positive 0.0625. Well, those are off by a factor of 10. 0.5 squared times 0.9. And that's negative, so it's going to be negative 0.225. And then 8.1 times 0.5 is 4.05. And then plus 9.2. So let's add all this up. 4.05 plus 9.2 plus 0.0625 minus 0.225, and then this tiny little insignificant amount, but I'll put it in there anyway, plus 0.00625. Oh, I hope I didn't screw this up. So this is approximately 13.1. I'm just doing 1 decimal place. So that's going to be right here, negative 0.5. And then 13.1, which is right about, I don't know, right about there. All right, we got one more point. Negative 2.25. Oh, gosh. One more point. So we got f of negative 2.25. This is why I don't do the y values on every problem. right? Only on the ones that insist upon it. So we got 2.25. Doesn't really matter that it's negative because the power is the fourth power. Oh, shoot. So you get 25.62, blah, 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 blah. 628, I guess. Oh, shoot. Oh, I'm tired. I forgot to multiply it by 0.1 times 0.1. So it's 2.5628, blah, 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 blah. All right, so I got 2.25 to the third power. And then times 0.5. And then it is negative, but it's negative times a negative, so it's going to be positive 5.6953. 2.25 squared times 0.9. That's negative now, 4.55625. And then I've got 8.1 times 2.25 negative. So that's negative 18.225. And then finally plus 9.2. So I'm just going to start adding these up. I've already got that one in my calculator. So plus 9.2. Cross them off as I go. Minus 4.5562. Plus 5.6953. Plus 2.5628. And I get negative 5.3. All right, so we're over here at 2.25, which is just a little bit past negative 2. We're going what? We're going negative 10, I guess. So it's going to be right about there. All right, because this is negative 10, so this is negative 5. Close enough. All right, and this is negative 2. All right, now remember, this was a minimum. Yeah. This was an inflection. So it's changing its concavity. Actually, no, hold on a second. Let's get this straight. Negative 2.25 was a minimum. Then this was an inflection. So that's our graph. And let's make sure everything makes sense. So this is negative 2.25. This is negative 0.5. So we have concave up. Good. Yeah, concave up. CU from negative infinity to negative 0.5. All right. Then again, from 3 to infinity. Yeah. Then we have concave down from here to here. I know I'm stretching it there, but that's concave down, CD, from negative 0.5 to 3, concave down. We have increasing from negative 2.5 2.25 all the way to infinity. All of this is increasing. And then we have decreasing from negative infinity to negative 2.25. And we have a local min. Let's write that over here. Local min of negative 5.3 at x equals negative 2.25. And no local max. DNE for the local max. There is no top of the mountain. There is no highest point. I should mention, I think I have mentioned this before, that arrowheads don't really exist. It's just a figment of our imagination. The graph just goes right off the edge of the screen and off to infinity. But that's a heck of a problem. You know, if you get a problem like this on a test, you would really want to, you know, budget your time wisely. I think on the next test, there'll be less problems because this graphing stuff takes a while. And I might even supply you with some, you know, hints and little tips that will help make the time go a little bit faster. But until then, that's all I have for today. So I'm Dr. Jordan, and I'll see you on the internet.